It's time for day 13 of Advent of Code. And for today's problem, we are looking at, we're parsing packets. And this one's a little easier than, say, the binary packets problem from last year. I reviewed that one on the blog maybe no more than a month or two ago. But really, we have these packets, and they can be recursively defined. Each packet is either an integer or it is a list of packets. And so we can have, a list of integers. That's a valid packet. We can also have a list of lists of lists and lists, and the nesting can just sort of go down. We can also have empty lists, which is an interesting case for us to deal with. But the first part of the problem, our input is given to us in pairs. So we take, this is our first pair of packets, this is our second pair of packets, and they're separated by spaces, and we have to determine, how many of these packets are in the correct order, how many of these pairs are in the right order. And so we have this complicated mechanism, a few different rules for saying, is this packet less than another packet? So if we compare this one, 11311 versus 11511, well, it turns out this one is in fact less. It comes before, because we look at when we're comparing two lists, we compare the elements, index by index. We get to here and say, 3 is less than 5, so therefore it's less. When we compare a single integer to a list, we just raise that integer up, put it in a singleton list. That's how we compare. When we compare empty lists to other things, when one list runs out beforehand, so in this case we are comparing an empty list to a singleton list of 3, we say the empty list is less than the singleton list. So really what we have to do, first part, how many of these pairs are in the right order already, and we just count up their indices and add all those together. In the second part of the problem, what we're going to end up doing is we want to sort all of the packets we are given, and then we want to insert these two divider packets into that sorted list, and then we just want to find the final indices of those divider packets and multiply them together. So things worked out really, or pretty nicely for me in that. We'll just look at the code and we'll see why things worked out pretty nicely. Haskell ends up working well for this problem, I think. There are a couple gotchas, but I think Haskell makes it really easy for us to deal with them. So let's look at how to parse all of this. We will start with a packet type, and Haskell is nice for this because we just make a sum type. We have the int packet constructor and we have the list packet constructor. Very easy to keep those separated, and then we can write this recursive function for parsing an individual packet, which can be either of these cases. So we have either the parse integer case or we have the parse list case. Parse integer, obviously very simple. We just parse the number and we wrap it. While parsing a list, what we do here is we say, okay, give me the left bracket, and the right bracket will be at the end of this. In between, we get our packets, and we use sep by, not sep by 1. We actually want to allow for empty lists, so very important that this is sep by. And then we recursively call parse packet within here, so that we get a list of packets, and we separate them by just the comma character. And so if you're used to just sort of taking a string and converting that into inputs, recursive parsers are actually a little bit tricky. You need to keep track of some of the state, and it gets more complicated. The parsec limit does that for us, so really nice and convenient. So now we'll have parse packet pair. This is very easy. We just parse each packet with end-of-line characters in between, and we separate this parser by end of line as well. I had to make sure that my final line had that end of line character in order for this to work properly, but that's a fine addition as far as I'm concerned. So let's move on to the algorithm. Where we really want to focus our efforts is, okay, how do we compare two packets? This is where most of the conditional logic happens. So we just have to apply all of the different rules that they give us in the problem. So if we have two int packets, actually, one important note about this function. At first, I had this return a Boolean, just say, okay, are these two packets ordered correctly? But even while I was doing part 1, I realized we want this to return ordering, because in the case where we're comparing lists, we need to ask, okay, if it's less than, we're less than. If it's greater than, we're greater than, just looking at those first 2 elements. But if the first 2 elements are equal, we're going to need to recurse. And so we need to be able to make the distinction of, okay, what ordering is occurring. And as we'll see, this works really well to return an ordering here for part 2. So when we compare 2 int packets, that's very easy. We just use the compare function on the underlying integers. That gives us the ordering we want. Now we have these 2 intermediate cases where one of our inputs is an int packet and the other is a list packet. In this case, we raise the first one to be a list packet that has a singleton and then compare it, or just recursively call eval packets. It feels a little weird because we're making a recursive call, and elevating the int packet to list packet feels like it's, it feels like we're growing our stack, which could potentially be infinite recursion, but it's okay, it works out. So we do the same thing in this case as well. We lift the second one as a list packet. And now we have to compare the final case where we have 2 list packets. So now things sort of break down depending on which of these are empty. So if we compare, okay, packets 1, packets 2, let's say they're both the empty list. These are equal. Now suppose the first one is the empty list, but the second is not. That's less than. Conversely, greater than if the second is the empty list. Now we have to consider 2 non-empty lists. And we'll compare the first packet in each of these lists, recursive call, eval packets. And as I said, we need to consider, okay, if these first packets are equal, then we need to recursively call on the rest. Otherwise, we can just return the first comparison. If it's less than or greater than, then we're done. We can just return that. So how do we apply this function? Well, in the first part, what we'll do is we'll take our input packets, we'll zip them with the indices. So remember, it wants us to add the indices of the pairs that are correctly ordered. So we're just going to zip 1, 2, that list comprehension with these. We're indexing from 1, not 0. And we're just going to track with our fold type. We're going to track the final score because we're just adding the index over and over again. So all we do, we just say if they're in the right order based on the evaluation. All we care about is if right order is less than, then we add the index. Otherwise, we'll just return the previous value. And that is enough basically to get us our first solution. So for the second part, we have to sort all the packets, except that we also want to introduce these divider packets. So showing quickly what these look like again, we have 2 nested in a couple lists, and we have 6 nested in a couple layers of lists. So we'll make those divider packets. We'll just create a new pair for those and just append that to our original list of inputs. And we just use a little helper here, turn the tuple into a list, and then we can concat all of those lists together so we get all our packets in one list. And now it's really convenient. We can just use the sort by function with our eval packets because it already is the right form. It takes packet, and returns an ordering. That's all we need for sort by. So now we just need to find the element index of the first divider and the second divider. Assuming those both exist and we get just as the result of lem index, we just multiply those indices together, although lem index will give us something that is a 0 basis index, whereas we want a 1 basis index, so we do have to add 1 to both of these. But then we'll get our correct answer, and that is pretty much it. These are sort of the test cases I wrote. Nothing too big about the scale of the numbers in this problem here, so I'll just run my test. My test is starting to take a bit longer, I think, from the accumulation of the different days, but maybe I'll have to comment them out so I can go a little faster in the future days. But all the tests are passing, so we are over the halfway mark. We're more than 50% done with Advent of Code this year. So, well, at least in terms of numbers of problems. In terms of difficulty, we might not be there yet at all if we factor that in. But if you're enjoying these videos, make sure to subscribe to the Monday Morning Haskell mailing list. That link is in the video description below. And while you're at it, make sure you subscribe to our YouTube channel if you're enjoying these videos. So thank you so much for watching, and I'll see you tomorrow.